I'm very glad to see you back today. Yesterday we did chemistry, so today we're going to move on and we're going to do a little bit of physics, right? So if you turn to page 10, we are going to look today at work, energy, and power. Now, some guys find work, energy, and power very difficult. It might be because you've got a little bit of problems with components that we did in grade 11, right? It might be that there's a lot of different memos because there's different ways to do things. And then you are taught a specific way in class, and then you come to the memo, and the memo looks different. Right. I'm going to try to show you today why the memos are different. What is the different ways that they approached it? So we're going to look at work, energy, and power, all of that, everything you have to know about work, energy, and power. And then we're going to just look at what happens when I put the momentum equations with that. Which one do I have to choose if I'm doing bigger problems? So we're starting out on grade 10, and as always, we're starting out with a definition that you've already learned by heart. Hey? We talked about work done. Now, if you look at the definition there's some unexpected things in a definition. And when you learn a definition, go and look at the unexpected, because that's the thing that you're going to forget. So if you look at this one, it is the work done on an object by a constant force. Now, there you have constant force. That is a little bit unexpected. Constant force is F delta x cos theta, where F is the magnitude of the force. There's something else that you have to look at, magnitude. Delta x is the magnitude of the displacement, and theta is the angle, and what is important, which angle? The angle between the force and the displacement. Now, learning the definition by heart is one thing, but applying it is something else. So we have to know how to apply it. So if you take say, for instance, a crate on a horizontal plane, and you are pulling it to the side with a force F, you're pulling it 3 meters, say the force is something like 10 newtons, and they ask you, what is the work done by this force? Then we're going to say, the F now is that applied force we are working with. Delta x is the displacement, and then you have cos theta. So the force that is applied is 10. No components, nothing. We're using the magnitude, and the magnitude is 10. Fine. Delta x, how far is the displacement? 3 meters. And then you get to cos, and then we get to the angle. And what is the angle? It is the angle between the force and the displacement. So you put your pen in the direction of the force, and you turn it until you get to the displacement direction. Which is the displacement direction? It's also to the right. It's being displaced to the right. So how far do I have to turn my pen? Nothing. So now the angle is 0. Right. And there's a few things, if you know it, that make it easier. What is cos of 0? 1, yes. And cos of 90? 0. And cos of 180? -1. It helps if you have that in your head, because then it helps you to know. You don't even have to work out the cos theta. You know immediately it's 1. It saves you calculated time, but also it helps you to understand better. Now we get an answer of 30 joule. Now if you get 30 joule and it's a positive, what does that positive imply? Not direction. The thing about energy that we measure in joule, it is a scalar, it's not a vector. If you go to the shop and you buy an energy bar, do you buy 340 kilojoules right? Huh? No. Energy doesn't have a direction, right? Otherwise you would have a problem if you're going to run a marathon. Just make sure you always buy the forward ones, hey? Energy doesn't have a direction. So energy's got no direction, but now we're doing work. And now we have a positive and negative. What does it mean? If it's positive, it means we are putting energy into the system. We're making the energy of the system more, right? So if you do the same thing now for the frictional force being to the opposite side. Let's say we've got a friction force of 1 Newton. Now I'm going to say the work done by friction will be the frictional force delta x cos theta. And now the whole magnitude of the force, 1. The displacement, 3 cos. And now I put my pen in the direction of the force I'm working with, and I turn it until I get to the displacement. How far am I turning it? 180. And what do we know about cos 180? It's just minus 1. So this will end up as minus 3 joule. Right, what is the minus? It does not mean in the opposite direction. It means this force is removing 3 joule energy from the system. Is that right? No. Good. So this was easy because it was in the horizontal plane. Let's take one where we do the same thing but take a force that's acting at an angle. If we take one that's acting at an angle of, say, 30 degrees there, if, let's say, 100 newtons, and we've still got a frictional force of, say, 20 newtons, and now I'm moving it 3 meters, now we can do the same thing. They can ask us, what is the work done by the applied force? There's always F delta x cos theta. If it's the work done by the applied force, that F is the applied force, and that is 100. And you don't go working out components. Go back to your definition. The definition say the magnitude of the force. It doesn't say anything about components, right? You use the whole 100 newtons. And then delta x is the displacement, 3 meters. And then you get to cos, and that angle is between the force and the displacement. So put your pen in the direction of the force and turn it until you get to the displacement. How far are you turning it? 30 degrees. Right. And then you get a positive, now I don't even have my calculator with me, a positive joule. Right. What does the positive mean? It's putting energy into the system, right? It's putting energy into the system. So whenever they're asking work, go and check the work of which force. You have to know which force you're working with. It's not always the applied force. It can be the frictional force. It can be the normal force. It can be the gravitational force. So if you look at this one, gravity is working down and the normal force is working up. What is the work done by gravity? Now, once again, you have to have the force, the displacement, and cos theta. Now, you will have the force, you will have your 3 meters, and you will have cos. What will be the angle for the gravitational force? Put your pen in the direction of the force and turn until you get to the displacement. How far am I turning? 90. And what do we know about cos 90? It's 0. So whenever you have a force that is perpendicular to the displacement, immediately the work done by that force is 0. Right. And remember, don't just write 0. You still write 0 joule. Just remember to keep writing the joule. Now, how about the normal force? What will be the work done by the normal force? Also 0, because it's also perpendicular to the movement, right? So whenever you do that, remember, for the Department of Education, you don't even have to write the forces if you add them together that are 0. Something that's 0 you don't have to put in, but this you will have to work out if they ask you. Everyone happy? Right, now we're doing one on an inclined plane, and that's the one that's a little bit more difficult. So I put it for you on page 11. So let's just look at that. And now we're looking at one where we were working with an inclined plane. Now I said in the example, a crate with a mass of 10 kilograms is pulled 4 meters up an inclined plane. So I'm pulling it up 4 meters, right? The angle with the ground is 30. And that's another thing you have to take away from this. As you read, go and check if what they give you in this wording is in your picture. If it's not in the drawing, add it to the drawing, because it's easier afterwards to see in the drawing the information that you need, right? So the 4 meters was not there, and I put it over there. Inclined plane makes an angle of 30 degrees. that is there. The crate is being pulled by a force of 180 newtons and experiences a frictional force of 10. So that will be in the opposite direction. And now I ask you, calculate the work done by each of the forces working on the crate. So let's start with the first one. We start with the applied force. If you look at the applied force, it's acting in that direction. So the work done by the applied force will be F delta x cos theta. F is now the force 180, easy. Delta x, the displacement was 4 meters. And now we have to look at the angle. And how do I get the angle? I put my pen in the direction of that force and I turn it until I get to the direction of the displacement. Where is it displaced? It's displaced in that direction. So how big an angle do I have to need? 0, nothing, right. And then you get plus 720 joule. And what does the plus mean? The fact that it's positive tells you this force is putting energy into the system, right. Let's go on to the next one. If you look at the next one, now we're working with the frictional force. Frictional force, it's 10 joule. The movement, the displacement is 4 meters, and then once again, I put my pen in the direction of the force I'm working with now. I'm working with friction, it's working down. And then I turn it until I get to the displacement, and that is 180. And what do we remember about cos 180? Yes, -1, so that gives you -40. And what does the minus tell you? That frictional force is removing energy, right? It's removing energy. It will be slowing down the system. Right, and then we get on to gravity. Now this is actually, with an inclined plane, gravity is the one that is difficult, right? Now, if you work according to this definition, I'll show you the alternatives later on, but if you work according to the definition, we said the work done is F delta x cos theta, and we're working with gravity. So remember, not the mass, it's the mass times 9,8. That's one of the things that you get wrong. Then times the displacement, that is 4. And then cos, and now what do we have for an angle here? The angle is the difficult one. What do I have to do? I put my pen in the direction of the force, and then I turn it until I get to the displacement. So what do I need? I need that angle. Now, if you think back, and this is where you have problems because you forgot about grade 11. Right? With grade 11, we worked out the perpendicular force, and then we said this one, this angle over here, is the same as that small angle over there. Right. Let's just go back and see why that is. If I extend this one, then I get a 90-degree angle down there. So if this is 30, and that is 90, and the inner corner should give me 180, that means that top one, 60. And then those two should together be 90 because they're perpendicular to each other. And then that gives you that one as 30. That was how we said that was 30. So that is grade 11. And now what do I have to have? I have to have the whole one. So it's the 30 plus the 90 on that side. So whenever it's moving up an inclined plane, that one will be the bottom angle, the theta will be 90 plus the bottom angle. Right. Because it's always the bottom angle is that one, and now I have to add that to the 90. So if it's moving up the plane, the angle will be 90 plus, and you use the whole gravitational force, no components. Right. How about moving down? Let's just take one where we say it's moving down. If you have that one, and everything is moving down, if it's moving down the plane, that angle was 30. Now, if it's moving down the plane and you want to work out the work done by gravity, we say, okay, what force are we using? We are using the gravitational force, so you work that out. Then delta x will be the displacement. And now the difficult thing is that theta. We are going back to the definition that we had on grade 10, and we're saying when you want to work out the work done, you have to have the force, the displacement, and cos theta. and theta being the angle between the force and the displacement. So what we did, we said, to work out the work done by gravity, if this thing is sliding down the plane and you want to work out the work done by gravity, the formula is W is F delta X cos theta. And that F is whatever force you're working with at that moment. So at the moment, I want to work out the work done by gravity. So the force must be the gravitational force, m times g, right? And then delta x is the displacement, but just the magnitude of the displacement. So there's no plus or minus. It's just if I am moving it 4 meters, then you have to put in there, that was m times g, 4 meters. It's just the magnitude of the displacement. And then you get to cos delta x. And in your definition, they tell you that angle must be between the force and the displacement. So we put our pen in the direction of the force we're working with at this moment and turning it until you get to the displacement. So how far am I turning it? Now, if you think back, when we had a horizontal force, a horizontal plane with a force like this, we said if we work out the work done by the applied force, we put our pencil in the direction of the force, we turned until we got to the displacement. So there you had to turn it 30 degrees. We said if we worked with friction, friction is in that direction. So you have to turn it from there right over to the displacement. So if it's moving in this direction, that's the displacement from the force to the displacement. You had to do that, and so for friction, the work that you do is always cos 180. It's always in the opposite direction, right? And if you work with gravity here, gravity was perpendicular to the movement, and then you had cos 90, and cos 90 is always 0, right? So then we went to the inclined plane, and when we got to this one, we said on an inclined plane, if you're working with the force that is applied, then that force is in the direction of the movement, because this thing is moving up the slope. So there you had to use cos 0, because the force was in the direction of the movement, right? And then we got to friction, and with friction, we said friction is working down the plane, but the movement is up the plane. So how far do I have to turn? 180 degrees. So there, it was cos 180, right? So still on page 11, we now work with gravity. And we said gravity is working straight down. And if you want to have the angle that you have to use here, remember the angle is between the force and the displacement. So you put your pen in the direction of the force and you turn until you get to the displacement. So over here it would have been 90 up there plus that angle that we in grade 11 said is the same as the bottom one, which is 30. So whenever it's moving up the plane, then the theta that you will use is 90 plus the bottom angle. So no components, no components. We're using the whole magnitude of the force and the whole magnitude of the displacement. And then we have to just make it everything right by using the correct angle. So if you were going up the slope, then the angle was 90 plus the bottom angle, because you had to have that whole one over there, right? But now in this new one, we are moving down the slope, right? And that's the one I asked you to look at. We are now working with gravity. We want to have the work done by gravity, but gravity is working like this, and the displacement is now down the plane. So I put my pen in the direction of the force and I turn it until I get to this displacement. So what do I need? I need that as my angle. Is that right? Okay. And what is that angle? Well, same thing we did now. This is 90, that is 30, and together they must be 180. Right. So that one will be 60. Or what we did before is we said that one is also 30. Remember, it repeats over there. So what you can say is when you're moving down the plane, then theta will be always 90 minus the bottom angle. Right. So if you are moving up the plane, then theta should be 90 plus the bottom angle. But if you're moving down the plane, then you're looking for that angle, and that will be 90 minus the bottom 30. Okay, and that makes it easier. Right. Okay. So that was for gravity. And now the very last one we have there is the normal force. So for normal force, it will be normal force, displacement, and then cos. And between the normal force and the movement, the angle is 90. And cos of 90 being 0 will give you no change in the energy of the system. Right. And remember, we also said if something is positive, if the work done is positive, it means you're putting energy into the system. If the work done is negative, it means you're taking energy out of the system. Like friction, it's moving, it's working against the system. It's taking energy out of the system.